We continue with case 3 of our capacity demand time formulation. Up to this point, we have looked at the loads occurring with random magnitudes as pulses, but the number of pulses are known. We relax that assumption now and let the loads occur according to a Poisson pulse process. The rate is lambda per unit time. As before, the magnitude of the pulses are IID and they are independent of the capacity. The capacity still is considered not to degrade with time. We are going to relax that assumption next in this lecture. But so far, at this point, C of tau is a random variable C0, so there is no aging. And the loads are Q1, Q2 all the way up to Qnt, and each of the Qs has the same distribution, Fq, and they are mutually independent. The very important point to note here is the subscript Nt on the last Q. That N is a random variable. That's why it's uppercase, and it signifies that the number of loads occurring in the interval 0 to t is not a known number. It's a random variable, and specifically in this instance it's a Poisson random variable because the underlying pulse process is a Poisson process. So how can we set up the expression for reliability, and how can it simplify our computations? So let's start with the basics. The reliability function is the probability that Q1 is less than C0, Q2 is less than C0, Q3 is less than C0, and all the way up to Qnt is less than C0, but Nt now is a random variable. So earlier in the previous case where the number of loads was not random, we were able to simplify this by conditioning the reliability on an arbitrary value of the capacity. Can we do something similar? The problem is now the number of loads is random as well, so that makes matters a little more complicated. So we are now going to bring in the theorem of total probability in 2 steps. So let's go through those. So we can first express reliability by conditioning on the number of events. So let us fix capital N at small n, and with that conditioning we can write the probability of all the intersecting events, and then total probability lets us sum it over all possible values of n and multiply with the corresponding PMF of n. So that's how the sum n going from 0 to infinity comes. Now we can further condition this and then remove the conditioning by total probability on C0. So you see the second conditioning event now, n capital Nt equals n now has a companion, that is C0 is equal to little c. And you see that that is now nested inside an integration on c going from 0 to infinity, all possible values of c that is, and weighted by the density function of C0. So this gives us the unconditional reliability as a function of time by conditioning on number of events, number of loads, and the random capacity. Let's now simplify this step by step. So the probability that the intersection of the events Qi less than little c, that we can raise to the that can be expressed by raising the CDF of Q to the power of n, because that intersecting events are conditioned on little n and little c, so we are able to raise FQC to the power of n. And obviously we can't forget that there is a sum and there is an integration outside that kernel. Let's proceed to the next step then. We have now we will bring in the expression for the PMF of capital N. That is the Poisson PMF. So n going from 0 to infinity, and the Poisson PMF is exponential minus lambda t times lambda t to the power of n divided by n factorial. So that is the Poisson PMF, and that is multiplied by fq to the power of n, and that is summed from 0 to infinity. Now we can put together the two expressions raised to the same power n. So we could write lambda t fq at c raised to the power of n divided by n factorial, and that quantity summed from 0 to infinity is another exponential. So if we equate that, if we bring that simplification, so we are left with, we get rid of the sum. The exponential minus lambda t was there from the beginning. The sum of the quantity raised to the power n divided by n factorial gives me another exponential, and that's exponential lambda t times fq at c. So this is a very interesting expression. We now can simplify further as exponential minus lambda t times 1 minus fq. That is fq bar, the complementary CDF of q, 1 minus fq. So very nicely we express the reliability as an expectation of an exponential term with respect to the capacity, the initial capacity C0.